Dehn-Sommerville spaces. It's a very rich topic, and before I move back to my office next week, I have here the opportunity on a larger board to show the richness. There are many, many connections to different parts of mathematics. Green is what is new, so there are a few new things this week. I was looking at the higher characteristics of Dehn-Sommerville spaces. The Dehn-Sommerville spaces are more general than manifolds. So here's the definition again. We are in the class of simplicial complexes, which is a little bit a special case, you know, of a delta set. Delta sets form a nice topos, and so you can do much more there, but that's good enough for many things. We have a very simple axiom system, just one axiom, finite set of sets closed under the operation of taking finite non-empty subsets. Then there is the notion of manifold, which we have talked about a lot. 4 years ago, for example, I made a list of 10 theorems which hold for Q manifolds with this definition here. Now, if you look at the Dehn-Sommerville Q manifolds, which are a little bit more general, the sense that we have no homotopy contractibility involved, it's a simpler definition, and so somehow natural, and most of the theorems really work, almost everything. The exception is the case of the Hamiltonian graph property. So every simplicial complex defines automatically a graph where the sets are the vertices and you connect to if one is contained in the other. And so you can look at all kind of graph theoretical things, like you can look at whether the graph is Hamiltonian, you look at the chromatic number, and it turns out also the chromatic number estimate, which we have for manifolds, holds also for Dehn-Sommerville spaces. So for two manifolds, for example, that would give you 6 here. For two spheres, we know it is 4. We don't yet know. We don't have a 2 manifold yet where it is equal to 6. It might be 5. So it's quite an interesting playground, and for me, it's just very beautiful to have this symmetry, this Dehn-Sommerville symmetry, which I realized first around 2009, 2010, when I started with this whole thing. I looked at the curvature, this curvature here, which is a discrete analog of Gauss-Bonnet-Cherm. This curvature turned out to be always constant 0 for odd-dimensional manifolds. And I could not explain this using Poincaré-Hopf, also something, 13 years ago, I developed 13 years ago, the index expectation, which is coming from probability theory. The expectation of the indices are curvature. And so you can explain quite well why this is flat, especially with the symmetric index here, which I'm very fond of. We have the notion of unit sphere, which is defined here. So a simplicial complex naturally has a topology involved. It's a finite set, and so on this finite set there's a finite topology. This finite topology is generated by a basis, which are the stars. And so it's an unhoused-off topology in positive dimension, but it's nice, a nice topology. And then you have the notion of unit sphere. I like to see this as part of differential geometry, as part of classical mathematics, and we have a notion of sphere, and these unit spheres allow us to talk about things like we have this beautiful formula, the sphere formula, which the unit spheres of even-dimensional points and the unit spheres of the odd-dimensional points are kind of cancelling out. This is true in general and implies especially that if the Euler characteristic of every unit sphere is constant, which we assume here, right? For a Q manifold, we assume that the Euler characteristic satisfies the law of Euler's J, right? This Euler-J formula, which is directly follows from the definition of what a Q manifold is. But here we ask that, so that's the assumption. And every odd-dimensional Q Dehn-Sommerville Q manifold is automatically a Q sphere, a Dehn-Sommerville Q sphere. So it has 0 Euler characteristic, it is flat, it has also 0 higher characteristic. These higher characteristics are very dear to me, and so there's also higher cohomology. The higher cohomology is different. So the higher cohomology is very complicated in general, but there is the Euler-Poincare formula, so we can express these higher characteristics also using cohomology. So that's new, that's just what I wanted to point out here. The proof is essentially the same, just using this green identity. I wrote once an article 2.5 years ago about the k-point green function. Yeah, maybe just as a review, we have this kind of elegant approach to Dehn-Sommerville. I like to kind of start with this simplex generating function which satisfies Gauss-Bonnet, a very beautiful formula which holds for any simplicial complex, and this shows us that the functions at unit spheres, kind of properties of functions, symmetries of functions at unit spheres, are inherited for the function itself of the space. So this is the derivative here. So we can also integrate that. Also, we can use Gauss-Bonnet also for valuations. Where are they? So here, so we have valuations. Valuations are, you know, like generalized Euler characteristic. It's something which behaves like a measure, counts, that it has this inclusion-exclusion principle, and this is a Q+1 dimensional space, and there is a nice class of, a little bit messy, because it involves these binomial functions, these binomial coefficients, these valuations here have the property that just the curvature of this valuation is just a smaller version of that, and that allows you just to see that half of the valuations are 0. And then you go to the barycentric refinement, which is a kind of a nice way to get closer and closer to the continuum. You apply, on the combinatorial data, you apply matrix A, and this matrix A transpose has eigenvectors which are kind of scale, which define valuations which scale, and so half of them then have to be 0, which follows from that. So this is a very convenient way to actually get these valuations. You just construct the eigenvectors of AT. So that's the relation. Here also, I think here on the functional level, you see very well why half of the F data are redundant for Dehn-Sommerville spaces. And that's the reason is because we have this, we can define this polynomial from from F we can define a polynomial H, and that polynomial H defines also F. So here we have a palindromic property of symmetry, like for Poincare duality for cohomology, which is also a palindromic property. But this is independent of that. So most of these Dehn-Sommerville spaces do not satisfy the Poincare duality. For example, these spaces, I like this class here. So we can take any graph, finite simple graph, and we attach to every edge, we attach a non-dimensional manifold. And then you just put the suspension and put that as an edge. And you put them all together. What happens is this is automatically a Dehn-Sommerville space, Dehn-Sommerville manifold. The reason is because every unit sphere here is a union of, disjoint union of odd-dimensional manifolds. An odd-dimensional manifolds are spheres. What I also kind of noticed just this morning is that actually there is kind of like the Swiss cheese theorem, which says that all manifolds are Hamiltonian. This is not true for Dehn-Sommerville manifolds. One of the properties which are not. So these manifolds here in general are not. And now you want to find the Hamiltonian path. So you start here, you go here, and then you continue here, you can go back. And you're not allowed to go here, you're also not allowed to go back here. And you cannot reach that point. So that's not Hamiltonian. So there are Dehn-Sommerville manifolds that are not Hamiltonian, in contrast to manifolds which are Hamiltonian. And that's what I wanted to say today.